Hey everyone, so today I have a 3.5-inch Western Digital hard drive that I want to just give you a little bit more information about, show you what the problem is, and yeah, we'll see if this will be an interesting video. So this drive came in, it doesn't have power. I'm not sure what exactly happened to it, but they said they plugged it into their computer, it doesn't turn on, doesn't do anything. So before I plug this into PC3000, I want to show you what type of PCB there are on these 3.5-inch hard drives, and just tell you a little bit about them, so that everybody's on the same page. Let's go ahead and open this thing up. All right, so this is the PCB for the patient hard drive. And as you can see, it does not have a ROM chip. So it does not have the U12 chip, which is where the head adaptives, micro jogs, etc., is stored. And that information is stored in the MCU, which is right here. And that's basically the difference between this PCB and, let's say, this PCB here. So this is a PCB from one of my donors, and as you can see the U12 EEPROM, as Lewis would call it, right there. The question then comes up: how do you replace the ROM chip if that's the case? Well, if this one's missing, right, what do you do? So this one doesn't have it. If this PCB goes bad, then what do you do? And the answer to that is you have to rebuild it from the service area. Now, the service area is an area on the platters that is not user accessible. So if you don't have the software to access the user area, you cannot read and write to it, right? So it's a area on the platters that is outside of the user area. So you have service area, which is SA, and user area, which is UA. Generally speaking, your software, whether it's, I don't know, RStudio, Victoria, or something like that, cannot read and write to the service area, and that's the main difference between PC3000, DeepSpar, and other recovery softwares that you have out there. So, well, in this case, we're going to have to take it step by step. What is it exactly that happened? What caused this drive to not show up? And a lot of the time, the customer doesn't really know. They always say the line of, well, it was just sitting there, and after that, it doesn't power on. Something had to have happened in between there. So let's figure out exactly what happened with this drive. And again, this is the patient PCB that does not have the ROM on it, so it does not have the U12 chip, and we will have to rebuild the information for that ROM chip from the service area and on the platter. So this is an internal ROM. They call this an internal ROM when you don't see the ROM chip here. So this has an internal ROM, whereas this has an external ROM that you can simply transfer. So if this PCB goes bad, I take this chip off, put it on another PCB, and put it back on the drive, and then you have data. So let's see exactly what is going on with this hard drive, though, because it's not as simple as a PCB swap. Please tell me you got all that. Okay, good. All right, let me just put these aside for now. So this 3.5-inch drive is now plugged into the SATA port 2, and let's see what happens. You get that? And let's see the current that it draws. Get that spike? Yeah. See? So clearly this has issues. This is shorted. There's a short somewhere or something like that. But let's see what it looks like with the donor that I have here. And this drive is perfectly fine. So let's see the difference in terms of the current draw.
So you're plugging in the donor, the one you plan to use as a donor right now?
Well, no. So this drive is not approved for what it needs, actually. So it's it needs to go back to the customer for approval. So if you get a image or a picture of the screen here, you see the difference. So this thing, the patient was drawing 2.5 amps, which is insane actually for a drive, whereas
right now?
a donor, yeah,
The donor, right.
yeah, exactly. So half an amp is basically what's average here when it starts up, that is, and then after that it dies to 0.25 amps, give or take. Yes, so 0.25 amps on the 12-volt rail. Well, what's the next step here? You want to put it back there, actually, so I can talk to. Generally speaking, we don't really know what happened to this drive that came in, right? So I usually ask the customer, you know, tell them, listen, what happened to this drive? Anything that you can share with me? Any information is useful. Basically, what that program was telling us is that this hard drive, the preamp is shot. There's no way to rescue, you know, this drive or get the data back without replacing the heads. A lot of the time, what happens is they use a external enclosure for a 3.5 inch, and they power it on with the charger that's not for that enclosure. So whether it's, you know, if it's a charger that's 12 volts or something like that, they plug in a 19 volt charger or something like that, or even higher. And that's what causes these things to go out. Now, this hard drive does have a bunch of fuses and TVS diodes that I can show you quickly. So this is the same PCB that we're dealing with. This is just not the patient one. This is one of my donors. As you see here, there's a fuse, there's a couple of TVS diodes there. But what happened in this case is whatever caused this went straight to the preamp itself. So it went through all of, you know, the fuses, the TVS diodes, even through the MCU actually, and it went straight to the preamp on the head stack assembly. This is what the preamp looks like. If you guys did not see the other video, this is a head stack assembly from another hard drive, not this one that I'm working on. And this little guy here, that one right there, is the preamp. And that's basically what's fried in this case. So what I think is this drive could have been plugged in to a computer that was not hooked to a surge protector or something similar to that. And this is the end result. So, you know, maybe, I don't know, lightning strike or something like that. And yeah, that's honestly the best guess that I have. I'm not sure what else it could be, but I do know that the preamp is shot on this thing. And based on the current draw that you were seeing there, there's nothing to be done here besides replace the preamp. And in this case, obviously, it's the head stack assembly. So normally you would build after you put a new PCB on. So this is the patient donor here. I take this, I put it on, and I'm able to read the service area. But I'm not able to read the service area in this case. So I'll quickly just plug in the donor PCB that I have. So you want to make sure that you match the numbers here. That number there. Zoom sucks on this, but I think they get that part. So you want to make sure you match this number here. This 206070153700. Not now, Kevin. I'm making a video. I'm shooting a video. Not now, you fuck. So yeah, you gotta match that number to the donor, which is this. So that was my patient. This is the donor. That's not the donor. You see what you did? You fuck. This is the donor. So yeah, you match the PCB numbers because it's Western Digital, generally speaking, has a lot of different PCBs. Like, it's so many to remember. I try my best to keep just a log of it in my memory to try and remember these things, but it's just too many. So I gave up some time ago to try and remember every single PCB for Western Digitals because there's just too many of them. Back to what I was saying with that. So we take our donor PCB, we put it on the patient hard drive. Not that you guys need to see this, but why not? To recap, again, this is just for the viewers who are on live stream right now. So this was a good donor hard drive. Look at the current draw here. So that's a nice, healthy hard drive. It arcs, and then it just goes out and smooths itself out. As you can see here, I can refresh, get ID, sector access, all the good stuff. There you go. Last sector. Oh, okay. This drive has some issues, but that's not the point of this video here. So, of course, typical, right? So let's plug in our patient with the replacement PCB. So this is the patient with the donor PCB. Look at that. Look at the difference between the two. So this is very similar to what Lewis uses in amp meter that you use, and it's really helpful because it gives you a lot more information than just putting your ear to the drive, right? Because there was no way I was gonna notice this drive did that in terms of the power draw with just listening to it. So I can't hear how much power draw it's taking or how much current or anything like that it's taking. This is definitely, this makes a tech's job a lot easier. Let's go back to finishing the rest of this, I guess, diagnostics. So let's go ahead and power this drive on. So this is still SATA 2, port 2. We already saw this current draw. We know what this drive is doing, but let's try to read the service area. So let's see what happens when we try to do that. So we're gonna hit auto detect.
This is the patient?
This is the patient with the donor PCB, yes.
So even with the donor PCB, it's taking 2 amps?
Yes, that is correct. Which means?
It's something other than the PCB.
Exactly.
Why do people always think it's the PCB when the drive isn't turning on?
And that's a problem because I don't know what it is. They generally...
Is it the hard drive version of, is it just a cable?
It's just a cable, exactly that. So, I mean, people always assume that it's the easier of if you give them 2 options, and they're always going to assume it's the easier of the 2 options. So, let's let's try to So when I try to refresh read ID, I can't obviously, but that's okay. We don't really need that. Actually, let me just start this in normal mode because that's what we need to work with here, not kernel. So we're going to do normal, we're going to do that.
If I had an HDMI splitter, then I could record your computer.
So this is what I was telling you guys about. So we're trying to read where the service area is, or starts in this case. And basically we're trying to read the service area because without access to the service area, you do not have access to the user area. And that's very important in data recovery. It's very important actually for people who are starting data recovery. So if we hit this little button that says read service area from the hard drive, we'll take a look and see in the my amp meter, I'm calling this, power monitor, whatever you want to call it. It spikes up to 2 amps again. And it keeps spiking up, keeps doing that. So at this point, it's definitely an issue with the head stack assembly itself. To be more specific, it's the preamp that's gone out on here. And yeah, look at all this fluctuation here. By comparison, if I do, let me just quickly cancel this. Let me just here. I'm just going to plug in the good donor hard drive and quickly show you the difference once more. Patient here, donor. There.
Donor is much prettier.
Donor looks much prettier, much evened out. That's basically it. So I don't really know what happened to this drive. We don't know if it's, a bad charger that caused it, or something that was plugged into it, or it was plugged into a PC that wasn't plugged into a surge protector or something similar to that. But we do know that the preamp is fried on this thing, and this would have been a bit difficult for technicians who don't have the software that I'm using, the power monitor. It's not as straightforward because you always think, well, if I put it in kernel mode, can I do something else with it? No, because then you compare the graphs and you'll see right away one is drawing a lot more current than the other, and that usually answers the the question at hand. That pretty much wraps it up for today. I don't have anything else to show you guys or anything like that. So head swap, but I can do a head swap actually in this case because it's not approved. So yeah, sadly not. Also, I need a compatible donor. So this donor, here, this is the donor, this is the patient. So these two are a little bit different. They're not exact matches, But that may be okay. That, you know, that might be okay, and it might not be a big deal if I can match something called the micro jogs. Now, if you guys saw the last video that I made, it was matching the preamp revision, right? So the preamp number, revision, whatever you want to call it. On this one, you match something called the micro jogs, and micro jogs are basically parameters for the head stack to function correctly. That's all there is to it. I don't have approval to do a head swap on this one. I don't know if this is a compatible donor with this one because I have to check the micro jogs on this patient compared to the donor. I'm gonna wrap up the video here, just summarize what happened and take you through the steps that I took to figure out that this is just a bad preamp on the head stack assembly. So the first thing that I did was I took another PCB and I plugged it in here. Now, let's say I was not using the power monitor, the program that I'm using there with the PC3000. What I would do in this case is I would try to access the service area, see if it allows me to do that. If it doesn't, then I go into the power monitor, see what's going on, compare the two, right? You always want to have an identical drive, close enough, not an exact match, right, to compare your work with, to make sure that the system that you're using, the setup that you're using is all functional. So, and that's actually something that I stick by. I'm very strict when it comes to that. I want to make sure that I have a donor that I can always rely on, that I know works, and that I can use it as a base for the whole recovery process. That's pretty much it. So without the power monitor program, it's a little bit difficult to really get to draw a conclusion that it's for sure the head stack assembly. You can always make an educated guess. It's always going to be, well, you know, it's more than likely that the head stack assembly is bad. But with the power monitor software that I have there from PC3000, it's really convenient, and it gives me a lot more information that you wouldn't otherwise have. So that's, I guess, an essential tool, as Lewis would call it there. What's up?
The hazmat suit that Drive Savers uses overkill.
Yeah, actually. So, good point. Whoever brought that up, thank you. You reminded me. I didn't have to set this whole shit up again. So one thing about having, you know, hazmat suits or you know, a clean room, you know, so to speak, like a full-on, you know, clean room with vents in the ceiling and stuff like that, it's not needed. Why? Because this is a perfect substitution for it, right? If you want to get some info about this, I don't know, maybe they're interested. So this uses this is not a HEPA filter, this is a ULPA filter. It's an ultra low particle. It filters out smaller particles than a HEPA, right? And generally speaking, once you have something like this, you do not need a hazmat suit or anything like that, because the drive is going to be inside here. As you see, this one is not completed yet, so I normally bring this down to here. If you want to show them this one without zooming in too much. So I built this little thing here to close it when, you know, I'm using it, and it actually helps a lot in terms of the airflow. So the airflow is much stronger this way. There's no way anything's getting in this way. With this, maybe, I don't know, some particle does land here, just because the gap is so much bigger than there. So I like to close it maybe about you know, I don't know, 6 inches to here. So yeah, you don't need any hazmat suits or anything like that. That's mainly a gimmick to make their clients, whoever's sending drives into them, pay more. There's nothing more to it than that. It's sort of like a reason for them to charge more. Well, we charge you more because we have a lot, you know, more equipment, or we have, you know, a lot more you know, tools or something like that, or we use these suits or something like that. So it's obviously not needed, and it does not make the job any easier or any more difficult than it is. So that's it for today, and as always, enjoy your day.